Welcome to Chronicles of the Bioverse, where we uncover the fascinating stories of life and the natural world around us, from the tiniest nanoparticles to the vastness of the universe, making the minuscule monumental. In this series, NanoNarratives, we dive deep into the world of nanotechnology to explore its profound impact on our daily lives. Episode 1: The History and Evolution of Nanotechnology.
How small can you make machinery? Okay, that's the subject. Because I heard people around in the bath saying, tiny machines. What is he talking about, tiny machines? And I said to him, very small machines, and it doesn't work. I am talking about very small machines, okay?
That was the voice of Dr. Richard Feynman in his 1959 talk, There's Plenty of Room at the Bottom. In this talk, Feynman discussed the concepts on which the foundations of nanotechnology were built. But the term nanotechnology was only coined in 1974 by Japanese professor Norio Taniguchi. Professor Taniguchi described nanotechnology as the ability to exhibit control on the order of a nanometer, which is 1/1000th of a meter. To put that into context, a strand of human hair is between 80,000 and 100,000 nanometers wide. A single bacterium is approximately 1,000 nanometers long. Smaller still are hemoglobin molecules, with a diameter of roughly 5 nanometers, and DNA helices, which are 2.5 nanometers in diameter. Nanoscience integrates physics, biology, and material science to manipulate materials at atomic and molecular scales. On the other hand, nanotechnology enables the observation, measurement, manipulation, assembly, control, and manufacturing at the nanometer scale. But in order to visualize these tiny particles, one would have to zoom in at least 10,000 times. The development of the scanning tunneling microscope in 1981 by Gerd Binnig and Heinrich Rohr, however, officially marked the development of nanotechnology, since these tiny machines were easier to visualize. This truly remarkable machine is capable of distinguishing features smaller than even a nanometer, meaning that individual atoms can be imaged and manipulated using this device. When Dr. Feynman gave his talk in 1959, he described how he believed machines can be used to create smaller and smaller machines, all the way down to the nanoscale.
Now let's see what we would have to do if we wanted to write the entire Encyclopedia Britannica on the head of a pin.
And after gaining the interest of the scientific community, two approaches were developed for the synthesis of nanomaterials. The top-down approach essentially splits the bulk material, for example, a block of solid gold, into nano-sized particles by exposure to light or ions. Contrastingly, the bottom-up approach involves literally building the nanostructures one atom or molecule at a time through chemical reactions and physical methods. The fullerene, or buckyball, was discovered by Harold Kroto, Robert Curl, and Richard Smalley in 1985, 1 year before Binnig and Rohr were awarded their Nobel Prize for the development of the scanning tunneling microscope. The trio won the Nobel Prize in 1996 for their discovery. Fullerenes are very stable nanoscale carbon spheres. This marked the beginning of a new branch of carbon chemistry. Graphene tubes, also called carbon nanotubes, were observed in 1991 by Sumio Ehime and classified as members of the fullerene family. Carbon nanotubes are extremely flexible and strong, making them useful in many different applications. For example, they are used as composite fibers in polymer science to improve the mechanical properties of different types of polymers. When CDOTs were discovered in 2004, carbon-based nanomaterials became fundamental to nearly all fields of engineering and science. But nanoparticles and nanostructures have been around for much longer than you'd think. The ancient Romans may have been using these tiny particles centuries before Feynman's lecture in a special type of glass called dichroic glass. Dichroic glass is essentially two different types of glass used to create a single object that changes color in specific lighting conditions. This phenomenon of dichroism was, however, first fully explained in 1990 when scientists analyzed the glass under a transmission electron microscope and found silver-gold alloy nanoparticles. One of the unique features of nanomaterials is that their properties are dependent on their size. For example, the color of a suspension of nanoparticles changes according to the size of the nanoparticles. This feature was exploited by the Romans to create the dichroic glass, Michael Faraday made metallic gold suspensions in the mid-1850s, each with different colors depending on the sizes of the gold nanoparticles. IBM scientist Don Eigler and some of his colleagues used the scanning tunneling microscope in 1990 to create this image. What you are looking at are 35 individual atoms of xenon on top of a flat surface of nickel. Today, nanomaterials are used in many different fields ranging from computer science and engineering to biological sciences and medicine. Nanotechnology enabled us to create laptops instead of room-sized computers, and to design complex electrical circuits at incredibly small scales, like the ones that power our smartphones. Nanotechnology is vital in the advancement of semiconductors and computers. Transistors, for example, are only a few nanometers in size and are the building blocks of integrated circuits, which are crucial for computers. Making transistors so small that we can pack them into chips means we can reduce energy consumption and get better overall performance. The carbon nanotubes I mentioned earlier are used as interconnects between chips because they improve the speed of semiconductors. Quantum dots are semiconductor particles used in the manufacturing of semiconductors because of their unique electronic properties. For example, they are able to improve the efficiency of LEDs and solar cells. In biology, nanotechnology is being used in diagnosis, drug delivery systems, and imaging. Some nanomaterials even have antimicrobial and anticancerous activities. Not surprisingly, there are a plethora of nanopharmaceuticals available on the US market. Nanomaterials are also used as very effective drug carriers in medicine. Their extremely small size allows them to easily pass through the membranes surrounding our cells, meaning they can deliver specific drugs to specific intracellular targets. For a long time, nanomaterials were thought to be biocompatible with us humans, which is why we developed methods to exploit the properties of nanomaterials. But nanomaterials are still quite a recent discovery, so we don't really know the long-term effects of exposing ourselves to them yet. It is well known that nanomaterials are endocrine disruptors, which means they disrupt our natural hormone production and functioning. This is due to the fact that they can easily enter our cells. Once they're in there, they bind to all different types of receptors and change the activity of our cells. This is why many researchers find that nanomaterials affect reproductive and thyroid hormones. These hormones have intracellular receptors to which the nanomaterials bind. Mitochondrial damage is also caused by nanomaterials, and this is dangerous because it eventually results in apoptosis or programmed cell death. It has also been shown that nanomaterials may affect our gene expression. Because nanomaterials are used in so many different industries, and the fact that our demand for them is increasing as technology is advancing, these materials are ubiquitous and end up in our environments by pollution. This is why it is so important that we understand what the long-term health risks associated with these particles are. The global market for nanomaterials was, after all, valued at $7.78 billion in 2021. And this revenue is forecasted to skyrocket to $24.91 billion in 2030. One would think that these materials should be safe, right? As more research is being done, more is being discovered about these tiny little particles. Rats and zebrafish are commonly used as models to determine the effects of exposure to nanomaterials. In upcoming episodes, we will be diving into the effects of nanomaterials and what research is telling us about them. Thank you for watching this episode. If you enjoyed it, please consider liking and subscribing, and don't forget to turn on notifications so that you don't miss the next episode of Chronicles of the Bioverse.